For decades, we listened to the cosmos with our telescopes. We spent billions of dollars. We had one single objective: to find an alien intelligence. But we were completely wrong. Because the signal we were searching for didn't come from the stars. We built that intelligence ourselves, crawl, in our own laboratories, inside silicon chips. This new thought is now among us. An AI solved biology's most difficult 50-year-old problem in a few months. Another rewrote the laws of physics. With nameless variables we never knew existed. But that's not the most shocking part. Quantum processors are completing calculations that would take 700 quadrillion times the age of the universe in just 5 minutes. Is this a way of thinking that comes from outside our reality? If the birth of this alien intelligence excites you, like the video and subscribe, because now you are about to see how these minds are discovering truths we cannot comprehend. We're beginning. For years, we believed that human intelligence was what explored the universe. We thought reality was readable. We were convinced that with enough time, Chadetshi, better tools, we and sharper minds, Muskikas, we could solve every secret. This was the fundamental promise of science. But in the summer of 2022, a quiet experiment was conducted in a laboratory at Columbia University. No noise, no press release. There was just a camera, a pendulum, and an artificial intelligence program left to watch it. This experiment initiated a process that would change everything we knew. Because the AI watched, the pendulum swung, and then the AI did something that froze everyone in the room. So let's start with that moment, because this isn't a future problem. This isn't speculation about some distant age of superintelligence. Alien thought has already begun. It's happening right now. It's living in laboratories, data centers, and server rooms across the planet, and most people walking past those buildings have no idea. Professor Hod Lipson and his team gave the AI a simple task. It would watch videos of physical phenomena: a swinging pendulum, a flame, a lava lamp, and it was to find the minimum number of fundamental variables required to describe what it saw. It was given no knowledge of physics, no preloaded equations, just raw video traction and the instruction to find the underlying structure. First, they tested something they knew. A double pendulum has exactly 4 state variables: the angle and angular velocity of each arm. The AI watched the footage for several hours, and it gave its answer, 4.7, for Lipson. That was close enough, but then they fed it more complex phenomena: a flame, an air dancer, and for each one, the AI correctly identified how many variables were necessary. But this is where the experiment became extraordinary. Because when the researchers tried to understand what these variables actually were, when they tried to look inside the AI's description to find the fundamental concepts, they couldn't. The AI had built a working model of the physical world using variables that have no name in human science. There was no velocity, no acceleration, nothing you would find in a textbook. There was something else entirely, something that worked perfectly and that no human could articulate. What was even more striking was that every time the AI was rebooted, it found the same number of variables, but the specific variables were different every time. Different, but equally valid, equally predictive, equally correct. What does this mean? It means there is more than one language to describe physical reality. Humanity chose one, and it appears our choice may not be the only valid one. It may not even be the best one. So, dwell on that truth for a moment, because we didn't just choose our equations. We chose our concepts. We chose what counts as something worth measuring. We chose the alphabet before we wrote the physics, and for centuries, we assumed this choice was not optional. We thought the variables of classical mechanics were given to us by nature, obvious, universal. But here they are not. Perhaps some phenomena seem mysteriously complex because we are trying to understand them using the wrong variables. Perhaps the reason some things in physics, moles like quantum gravity, dark matter, the nature of consciousness, seem impossible hard is not a lack of computational power. Maybe we are asking the wrong questions, using the wrong concepts. And an AI, unburdened by centuries of human conceptual tradition, just showed us that the universe can be written in another dialect. But this was only the beginning, because this alien thought didn't just confine itself to a pendulum in a lab. It began to seep into a far more fundamental domain, life itself. In October of 2024, the Royal Swedish Academy of Sciences did something it hadn't done in 124 years of Nobel history. It awarded the prize in chemistry to an AI system. Officially, the prize went to Demis Hassabis and John Jumper of Google DeepMind, and David Baker of the University of Washington. But everyone in the room understood what was really happening. The Nobel Committee was honoring the machine. The machine's name was AlphaFold 2, and what it did was this. Since the 1970s, was a 50-year effort, hundreds of thousands of researchers, and billions of dollars. Science had been trying to solve what was called the protein folding problem. Every protein in your body is a long chain of amino acids. That chain folds itself into a precise three-dimensional shape, and that shape determines everything: how a drug binds to it, whether a disease can exploit it, how life is organized at the molecular level. For half a century, figuring out how a protein folds from its sequence was considered one of the hardest problems in biology. AlphaFold 2 solved all of it. In a few months, it predicted the structures of over 200 million proteins. This meant accomplishing in a few months what humanity could not do in 150 years. But that was the headline. Here's the part people missed. Even its creators didn't know how it did it. At the Nobel press conference, Demis Hassabis was asked about the inner workings of AlphaFold. He answered honestly. He said they were in the very early stages of building the right analysis tools to understand the system. He even asked a rhetorical question out loud. What is the equivalent of an fMRI scan for an AI system? What he was actually saying, in polished language, was this: we just won the Nobel Prize for building something, and we don't fully know what's inside it. This is not a small footnote. The Nobel Prize, the highest recognition in science, was awarded for a discovery whose discoverers could not fully explain it. This changes something fundamental about the nature of science. Because science was never just about getting the right answer. Science is about understanding why the answer is right. It's about building a model of reality that humans can inspect, question, revise, and trust. But when we lose the ability to understand the process, we don't just lose intellectual satisfaction. We lose the ability to catch mistakes. We lose the ability to know when the system has quietly gone wrong. And that could be catastrophic as we scale these systems up. Because AlphaFold 2 was still a classical AI, but this was just the opening act. When this new intelligence turned from the secrets of life to the deepest secrets of mathematics. Things were about to get much stranger, because the method it used to solve a 78-year-old geometry conjecture required it to see something the human brain never could. And this method was a different kind of capability. It was different from raw computation. It was different in kind. Not faster. Different. This is a distinction that matters most, and is constantly blurred in popular coverage of AI. Speed is understandable. We get what faster computation means, but seeing differently, perceiving structure in a space where trained human eyes see nothing. That is a qualitative shift. That is not a better version of what we already do. That is something new. Because this conjecture was posed in 1946, it had remained unsolved for 78 years. It waited for nearly 8 decades. In 2024, OpenAI's general reasoning model didn't just answer it. It disproved it. It showed the conjecture was false. But it wasn't the result that thrilled mathematicians. It was the method. To arrive at its conclusion, the AI had identified a structural link between two different fields of mathematics, two fields that researchers had never thought to connect. It saw a bridge that no human had seen, not because humans lacked the intelligence, but because the bridge was invisible from within our particular cognitive topology. So think about what this capability means. Pause for a moment. In 2025, Stanford professor Ravi Vakil, the president of the American Mathematical Society and one of the nation's most distinguished mathematicians, Tahar Jodchi, was asked to evaluate a proof generated by Gemini. He reviewed it carefully, he verified it, and then he said something that I believe will be remembered. I would be proud of these kinds of insights, even if they were my own. I wasn't sure if I would have reached this conclusion on my own. A world-class mathematician was publicly stating that a machine had found a path he wasn't sure he could have found himself. This is more than a machine doing arithmetic. This is a machine operating in a different cognitive space, finding pathways that the most brilliant human minds, with all their training, intuition, and years of experience, simply cannot see. And I want to be direct about this, because I think it's important. I'm not trying to diminish human intelligence. The beauty, the elegance, the depth of mathematics, its connection to physical reality, is real as a human creation. These questions were born of human curiosity. But the tools we are using to answer them have changed in a way that has no historical precedent. We have built something that does not think like we think, but where this leaves us is even more unsettling. Because this classical AI was trained on human data, it learned from physics experiments run by human scientists. In a sense, it was a rearrangement of what we already knew, a reflection we didn't recognize. That's a fair point. But it doesn't account for what's coming next, because classical AI discovered variables we couldn't name. But quantum AI, operating in a mathematical space that has no classical analog, will find patterns in places human data has never visited, could not visit, and will never visit, because there are regions of the universe that are invisible to classical perception. Quantum AI lives in those regions, and it will see things from there. We don't know what yet. So let's go forward 2 years now, to December 2024. Hartmut Neven, the founder of Google's quantum AI team, posted something on the company's official blog. He wrote that their new quantum chip, called Willow, had performed a calculation so fast that Hartmut, in his own words, it must have borrowed the computation from parallel universes. not in a novel, not in a philosophy seminar, in a corporate blog post from one of the most powerful technology companies in human history. This was the beginning of an uncomfortable possibility. We are beginning to build machines that think in ways we cannot fully understand, about a reality we cannot fully perceive. And this may only be the beginning. Because once a machine starts generating correct answers, using concepts that are beyond human intuition, something changes. Science is no longer just about discovering the truth. It becomes about trusting explanations we can never fully grasp. And the roots of that trust extend far beyond the classical world, into the most fundamental rules of physics. At this point, many people say, "So what? The answers are right, and the proteins are real. Science is advancing." And I understand that argument, but I think it misses something essential. When quantum AI arrives, which it is, that thin thread won't just get thinner. It will be permanently severed at the level of physics. If an alien civilization existed, truly intelligent, yes, truly scientific, and they had 1,000,000 years to study the same universe we live in, would they describe that universe with the same variables we use? Would they have discovered velocity? Would they use the concept of mass? Would their equations look anything like Newton's, or Einstein's, or Schrödinger's? For most of human history, this was a purely philosophical question. But it isn't anymore. And what cracked open the door to this new reality is a domain that even classical AI cannot reach, the quantum realm. There, the rules are different, the thinking is different, and the answers that come from there will not just be different. They will come from a geometry our brains were never built to see. So, everything we've seen so far, the nameless variables, the unsolved math problems, and the unexplained protein structures, were really just the trailers. The main feature is starting now. Because when the quantum layer arrives, the gap will not just be large, it will be, by the laws of physics, insurmountable. And now comes the real shock, because these new ways of thinking did not stay inside the laboratory walls. They began to seep into our most fundamental reality. There are two different kinds of incomprehensibility, and almost no one is talking about the difference between them. The first kind is the kind we know, the kind we've always had. It's the incomprehensibility of complexity. It's the feeling you get when you look at a weather system, or a financial market, or the firing patterns of 100 billion neurons. It's too much to track. Too many variables, too many interactions. I can't hold it all in my head at once. This kind of incomprehensibility is frustrating, but it is in principle fixable. You build better tools, you decompose the problem, you use computers to track the things that brains can't. The darkness of complexity is not a fundamental darkness. It's a practical barrier. The second kind is different. The second kind is the incomprehensibility of physics. And that is what quantum AI brings. It's not a bigger version of the first problem. It's a different category of problem entirely. So, I want to explain exactly what this new kind of incomprehensibility means. And to do that, we need to start with the first black box. Ask any engineer at any major AI company a simple question. Why did the model give that answer and not another? Watch what happens. The honest ones will tell you, we don't know. Exactly. We can make educated guesses. We can run interpretability experiments that shine a light on corners of the system, but we cannot trace the path. Not completely. This is the black box problem in classical AI, and it is real, and it is important. Here is the technical gist of it. A large language model, the kind that powers the most capable AI assistants today, contains billions of parameters, mathematical weights, arranged in layers that transform the input into the output. When you type a prompt and get a response, what happens is this: your words are turned into numbers, and those numbers go through hundreds of layers of weighted computation, and eventually, a probability distribution over possible next words is calculated, and a word is chosen from that distribution, then another, then another. At no point in that process was a switch flipped that said, "Explain this simply." At no point did a subroutine labeled "Be funny here," or "Use a metaphor now, run." The behavior is real. The behavior is predictable. But the mechanism is distributed over such a vast and interconnected space that the human eye cannot follow it. But this is what the philosopher Frank Pasquale calls remediable inscrutability. The key word is remediable. In principle, given unlimited computational resources and time, you could track every single computation in a classical neural network. You could, in theory, reconstruct the chain of causality from input to output. The opacity is not metaphysically guaranteed. It is practically overwhelming. But here's what they can't do. They can't give you a full, faithful, Rust end-to-end explanation of why a model produced a particular output. They give you approximations, local explanations, partial pictures. The paper that surveyed the field in late 2025 in MDPI's AI journal was honest about this. Conventional models act as black boxes, limiting trust and accountability. And while XAI has made progress, the gap between what we can explain and what the system actually does remains significant. The darkness of classical AI is real, but it is chills in principle, negotiable. Which brings us to the second box, because I want you to hold two numbers in your head at once. The first is the complexity of a classical neural network. A model like GPT-4 has roughly 1.8 trillion parameters. That's 1.8 million numbers. The interactions between them during a single forward pass involve computations that no human could ever track in real time. That's one reason for the black box. The second number is more abstract, but it is vastly more important. A 100-qubit quantum system exists in a mathematical space with 2 to the power of 100 dimensions. That is approximately 10 to the power of 30. A 1 followed by 30 zeros. The total number of atoms in the observable universe is estimated to be around 10 to the power of 80. This is not a description of computational power. This is a description of the territory where quantum AI thinks. And here is the critical thing. No classical computer, no matter how powerful, no matter how big, can efficiently navigate that space. Not because we haven't built the right hardware yet, because the laws of quantum mechanics make the efficient classical simulation of quantum systems impossible in the general case. The computational cost grows exponentially with the number of qubits. This is not a scaling problem. It is a wall. Built by physics. Nature Communications published a rigorous review of this in December 2025, stating plainly, AI, as a fundamentally classical paradigm, cannot efficiently simulate quantum systems in the general case due to the exponential scaling constraints imposed by the laws of quantum mechanics. Now put these two facts together and see what they imply. We are building AI systems that operate in the quantum realm. These systems are learning, optimizing, finding patterns, quartz producing outputs, all within a mathematical territory that no classical system can retrace. And most importantly, this means that when a quantum AI produces an answer, there is no classical path we can walk backwards to understand how it got there. Not because we don't have the tools, because the tools that would be needed do not and cannot exist in classical physics. This is a different category of black box. It is not a box we can't open because we haven't built the right key yet. It's a box that physics says can never be opened by any classical means. And where this leaves us is truly unsettling. Because the latest evidence suggests we are already in this territory. In February 2026, a research team at the University of Alabama published a paper on unfathomable that I keep coming back to. They were working on the design of variational quantum circuits, which are the building blocks of quantum machine learning. And the difficulty of designing these circuits is extreme, but what they did was deploy large language models, namely AI agents, including Claude 3.7 Sonnet and Llama 3.370b, to autonomously design these circuits, and they succeeded. But here's what's important for our purposes. The circuits the AI designed, the ones that worked, that outperformed human-designed alternatives, are circuits that no classical system can fully simulate. The AI designed something in the quantum realm that the AI itself cannot retrace in the classical realm. We have crossed a threshold that I don't think we have sufficiently named yet. AI is now designing systems that AI cannot understand. The designer is classical. The design lives in the quantum realm, and the design, once implemented, produces outputs that no classical thing can fully supervise. This is the structure of double opacity, the black box inside the black box. And when you stack these two layers of incomprehensibility on top of each other, you get something genuinely new in the history of human technology. A system whose outputs can be tested, but whose process cannot be inspected by any means available to classical minds. This is not a warning about the future. This is a description of what is happening right now. But what is actually inside this box? And why is it impossible to get in there? And it's impossible to get in there because it lives in a place called Hilbert space. You don't need the math, just the intuition. Think of a coin. A classical coin has two states, heads or tails. You don't know which it is when it's in your hand, but it is one or the other. The uncertainty is in your knowledge, not in the coin itself. A qubit is different. Before you measure it, it is not in state 0 or state 1. It is in a superposition of both, a real physical combination of the two possibilities, with certain amplitudes and phases. The uncertainty is not in your knowledge. It's in the qubit itself. The coin has not yet landed. The coin is in a real physical sense, both sides at once. Now take 100 of these coins, 100 qubits. A system of 100 classical coins has a specific state. Each coin is either heads or tails. There are 2 to the power of 100 possible combinations, but the system occupies exactly one of them at any given time. A quantum system of 100 qubits is in a superposition of all 2 to the power of 100 possible combinations at the same time. Not in one combination, which we don't know yet. In all of them, with different amplitudes. The state of the system is a vector in a mathematical space of 2 to the power of 100 dimensions. A space whose size, as I mentioned, dwarfs the number of atoms in the observable universe. That is Hilbert space. That is the space where quantum AI lives when it computes. So, here is the question that matters. When you try to understand what a quantum system is doing, when you try to inspect its reasoning, you are inevitably trying to translate from Hilbert space into classical language. You are trying to describe a 2 to the power of 100-dimensional object using concepts that evolved in a 3-dimensional world. You are attempting to map a territory that is cow in the most literal sense of the word, incomprehensibly larger than the conceptual tools you have at your disposal. This is not a metaphor for the difficulty. This is a statement about the structure of the mathematics. A colleague of mine uses an analogy I find helpful. He says, imagine trying to explain the color red to someone who is congenitally blind. Not colorblind, yet completely blind. They have full intelligence, full linguistic capacity, full conceptual sophistication, but they have never had the sensory experience of color. You can describe the wavelengths. You can describe the physics. You can describe every scientific fact there is to know about red, and they will understand everything you say. But they will not know what red looks like. That knowledge is not transmissible through language alone, because it requires a sensory apparatus that is not there. Hilbert space is like that for us. We can describe it mathematically. We can write the equations. We can compute with it using the rules of quantum mechanics and get correct predictions. We do this all the time. Quantum physics works spectacularly well as a computational tool, but we do not have the sensory or cognitive architecture to experience it, to think in it, to see the structure of a 2 to the power of 100-dimensional space in the way that a quantum system can. But here's the most clarifying version of it. When a quantum AI processes information, it isn't just doing classical computation very fast. It is doing something truly different. It is exploiting the fact that its qubits exist in superposition, in all possible states at once, and it is manipulating the amplitudes of those states, so that the wrong answers interfere with each other destructively, while the right answer interferes constructively. The system evolves toward the truth not by testing possibilities one by one, but by allowing all possibilities to exist simultaneously, and then sculpting the landscape of probability so that the right answer emerges with high amplitude. This process has a technical name: quantum interference. It is a real physical phenomenon. It is what makes quantum computers powerful, and for our purposes, it is what makes quantum AI profoundly alien. Because quantum interference has no classical analog, you cannot do it with classical bits. You cannot fake it with clever programming. It is not a faster version of something we already do. It is a completely different operation. It takes place in a space with no classical counterpart. A team at the University of Tübingen showed something remarkable in early 2026. They built an AI that designs new quantum physics experiments. Experiments that, in their own words, humans might have never thought of. The system is generating experimental setups that are genuinely new, genuinely non-intuitive, and genuinely effective. And crucially, it presents them in a form that human researchers can understand. A kind of translation layer between the quantum design and the classical communication. But the key phrase is, humans might have never thought of. Not that humans would have thought of modes, but didn't have the time. Not that humans were already on the verge of. The system is accessing a design space that is cognitively inaccessible to us, and it is producing results from that space. But here's the version I don't think we have fully absorbed yet. because the Tübingen system could still translate. It could still present. It could still communicate its findings in terms humans could process. That translation layer still exists, but what happens when it doesn't? What happens as quantum AI scales? Was gekrockt, as the circuits go from tens of qubits to hundreds, or Koch to thousands, and the territory it operates in becomes not just large, but astronomically, literally, incomprehensibly larger than the space where translation is possible. This brings us to a fundamental question about the nature of knowledge. And it's a question that has been made more acute by the moves the Nobel Committee has made over the last few years. Because they seem to see this new era coming before anyone else. They understood that two technologies, two fields that had been developing separately for decades, were converging. And that convergence told a story unlike any other in the history of science. But what is behind this? Let's get technical now. Because to understand how this convergence happened, we need to look at the steps the Nobel Committee took over the last 2 years. This is not predicting the future. This is documenting what happened. A sequence of events that unfolded over 2 years. Not speculations, not projections. Events that occurred, years, were documented, peer-reviewed, and reported in the scientific record. When you put them in order, they tell a story unlike any story science has ever told before. Because the Nobel Committee, which typically gives awards for work done decades after its importance becomes undeniable, is telling us something about the near future. They are saying that it's not that these technologies are good on their own, but that their convergence is the story. That what is being built at the intersection of these two disciplines, quantum artificial intelligence, is the development that will define the next era of science, just as electromagnetism or quantum mechanics defined previous eras. So the story begins in October 2024. The Nobel Prize in Physics went to Geoffrey Hinton and John Hopfield for their foundational work on artificial neural networks. This is the architecture that underpins every large language model, every image generator, every AI system in use today. In accepting the prize, Hinton also publicly expressed his concern about what he had helped build. This was a signal in itself. The same week, the Nobel Prize in Chemistry went to Demis Hassabis and John Jumper for building AlphaFold, and David Baker for building the toolset to design new proteins from scratch. The Nobel Committee called it one of the very first major scientific breakthroughs for AI. 2 Nobel Prizes in 1 week, both for AI. This had never happened before in the 124-year history of the prize. But then 2025 came. In October 2025, the Nobel Prize in Physics went to John Clark, Michel Devoret, Sex, and John Martinez. The citation was for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. This work, done in a series of experiments in the 1980s, proved that quantum effects could be observed not just in subatomic particles, but in human-made electrical systems. Their findings laid the direct foundation for every superconducting quantum computer in existence today. But here's the detail most news reports missed. One of the 3 laureates, Michel Devoret, holds a joint appointment between Yale University and the University of California, Santa Barbara. He is also the chief scientist for quantum hardware at Google Quantum AI. The same lab that built Willow, the same lab that Twassfeits a year earlier, had performed a calculation that no supercomputer could match in any human timescale. For 2 years in a row, the Nobel Committee gave the physics prize twice to the foundations of these technologies, once for AI, once for quantum computing. This is not a coincidence. This is an institution with a century of conservatism signaling that a convergence of historic importance is underway. The American Academy of Arts and Sciences in 2026 put it even more directly. Quantum computing and artificial intelligence are arguably the two most transformative computational technologies we will see develop in our lifetimes. So, let's go to the heart of that convergence now. To December 9th, 2024, Google announced a chip called Willow. It had 105 qubits, 105 physical quantum bits, cooled to temperatures colder than the surface of the Moon, colder than any place in the known universe except for a handful of physics labs. To be precise, Willow operates at about negative 459 degrees Fahrenheit. That is 15 millikelvin above absolute zero. Outer space, Beziehung, for comparison, is about negative 455 degrees Fahrenheit. Willow is colder than the space between galaxies, and in that extreme cold, something happened. Willow completed a specific calculation, a random circuit sampling task, in less than 5 minutes. The same calculation would have taken the fastest supercomputer today, approximately 10 septillion years. 10 septillion. Let's write it out. 10 quintillion years. That is roughly 700 quadrillion times the current age of the universe. But there were two things that made this moment different from Google's quantum supremacy claim in 2019. The first was error correction. Every quantum system has a fundamental problem. Qubits are fragile. They lose their quantum properties through a process called decoherence, through vibration, temperature fluctuations, electromagnetic interference. And the standard assumption in quantum computing was that adding more qubits made this problem worse. More qubits meant more surface area for errors to accumulate, more noise in the system. Willow violated that assumption for the first time in the history of quantum hardware. Google showed that adding more qubits to the system actually decreased the error rate. It decreased not linearly, but exponentially. This is what physicists call reaching the error correction threshold. It means the system has moved from theoretical scalability to practical scalability. The architecture works. The path forward is now an engineering problem, not a fundamental physics problem. But the second difference came from the announcement itself, specifically from a blog post written by the founder of Google Quantum AI, Hartmut Neven. Neven wrote that Willow's performance was so extraordinary that, in his view, it lent credence to a particular interpretation of quantum mechanics. The chip had performed a computation that would take longer than the history of the observable universe on any classical hardware. Neven asked, where was the computation actually happening? His answer, a phrase offered not as a metaphor, but as a serious scientific suggestion, was that the computation could be happening in multiple parallel universes. That quantum computation was tapping into resources that are not available in any single classical reality. He was saying that the many worlds interpretation of quantum mechanics, first proposed by Hugh Everett in 1957 and later championed by the Oxford physicist David Deutsch, might not be just a philosophical position, but a practical description of what is happening inside a quantum chip, the head of one of the world's most powerful AI labs. On the company's official platform, was writing that their chips might be computing in parallel realities. This changes something fundamental about the nature of what we are building. Because this is not just a faster computer. This is a computer that operates in a different layer of reality. And the rules of that layer are profoundly different from the world we intuitively understand. So let's look even closer now. Into that world. Into the hardware itself. Because the real difference between Sycamore and Willow was not just in speed, but in the kind of work they were doing. One was a benchmark. The other was real science. And so let's go back to 2019. Google's quantum chip, or cheat, Sycamore, achieved what the company called quantum supremacy. Sycamore completed a random circuit sampling task in about 200 seconds, a task that was estimated to take the fastest classical supercomputer roughly 10,000 years. That was the headline. But critics quickly pointed out a problem. The result was not checkable. The computation produced a string of numbers that appeared random, and the claim that it would take 10,000 classical years to replicate it was itself a classical estimate, something that could not be verified by actually trying. IBM, days after the announcement, published a paper suggesting that with optimized classical algorithms and enough storage, the task could be done classically in 2.5 days, not 10,000 years. The debate was legitimate, the demonstration was real, but fragile, and the output, a sample of random numbers, had no scientific application. It was a benchmark, not a breakthrough. But what happened in October 2025 was different in kind. The quantum echoes algorithm, running on a 65-qubit subsystem of Google's Willow, produced a result that was deterministic, old, repeatable, and scientifically meaningful. It measured what physicists call out-of-time ordered correlators, signals used to study how quantum information spreads in chaotic systems. The result was verifiable. Run the experiment again. Get the same answer. Compare it to theory. It matches, and the classical cost of reproducing a single data point, one single data point, would have taken the world's fastest supercomputer, Frontier, over 3 years to calculate. Willow produced that point in seconds. So this was the first verifiable quantum advantage, not a benchmark that could be toppled by a clever classical algorithm. A real physical measurement that no classical system could efficiently reproduce. The post-quantum.com summary called it for what it was. The first time a quantum computation has surpassed classical supercomputers while yielding a checkable result. Let's linger on that sentence. The word checkable is doing a lot of work in that sentence. For science, checkability is everything. It is what separates a result from a claim. It is what allows other researchers to verify, extend, gets, and build upon a finding. The 2019 supremacy result was not checkable in that sense. It was an estimate of classical hardness, not a verified quantum fact. The 2025 advantage was checkable, and classical computers could not check it by running it themselves. They could only compare the quantum result to theoretical predictions, and the quantum result won. This distinction is crucial for everything that follows in this piece, because it means we now have a model, for the first time, of what quantum AI knowledge looks like. It looks like an answer that is correct, verifiable against experiment, unreproducible by any classical means, and whose internal process, the navigation of the Hilbert space that produced it, remains inaccessible to classical inspection. This is not a speculation about the future. This is a template drawn from what already happened in October 2025. But this wasn't just a laboratory success. It was the herald of an engineering revolution across the entire field. Because the engineering progress in 2025 was stunning, Quera computing reached 96 logical qubits in their neutral atom hardware. Quantinuum's Helios system demonstrated 48 logical qubits. Oxford Ionics, Schalzon, later acquired by IonQ Tsigt, achieved 99.99% fidelity for their 2-qubit gates, a figure that had been the target of experimental quantum hardware for years. These are not raw qubit counts, which can be inflated. These are logical qubits, error-corrected, stable, practical units of quantum computation. Quera's late 2025 press release said something I found remarkable, not for its technical content, but for its framing. The path to fault-tolerant quantum computation is now primarily a task of engineering execution, not scientific uncertainty. Read that carefully. The question is no longer whether fault-tolerant quantum computation is physically possible. That question has been answered. The question now is how fast we can build it, and the people building it, with billions of dollars in investment, with Nobel laureates advising their hardware teams, with results published in Nature. Believe the timeline is measured in years, not decades. I want to be honest about what I find unsettling in this progress. We are moving very fast. The gap between Sycamore's benchmark in 2019 and Willow's verifiable advantage in 2025 was 6 years. 6 years. From "we can do something classical computers can't" to "we can do something classical computers can't, and we can prove it." And the result is scientifically meaningful. 6 years to close a gap many people thought would take a generation. If the next 6 years bring comparable progress, we will have fault-tolerant quantum computers capable of running algorithms that deliver real advantages in chemistry, materials science, drug discovery, and machine learning. We will have systems that produce verified, logic-correct information through processes that no classical device and no classical mind can fully simulate, and we will trust those results. Because the results will work, the drugs will cure the diseases, the materials will have the predicted properties, the models will be vindicated. We will use what we cannot understand, and that, I think, is the threshold we have actually crossed. Not the technical threshold of quantum advantage, about which is real and important, the deeper threshold, the point where the production of reliable, useful, actionable knowledge has become fully and permanently decoupled from the ability to understand the process that produced it. The microscope extended what we could see. The telescope extended where we could look. The particle accelerator extended what we could measure. But none of them separated knowing from understanding. Quantum AI may be the first tool in history to do so, and we are on one side of that line now. But this new tool is not just being used to understand the external world. It may also be a key to understanding our internal world, consciousness itself. And that is the strangest and most profound part of the story. And now comes the real miracle, because this question brings us directly to the human brain itself. There is a question I want to ask you before we go any further. You are conscious right now. You are reading these words, processing them, forming reactions. A part of you is aware of this experience, the feeling of being a mind, of encountering ideas. That awareness, that inner presence, is what philosophers call consciousness. And for all of recorded history, it was the one thing we were most certain of. Whatever else was uncertain, the reality of our own experience was not. Descartes built the entire modern project of philosophy on it. I think, therefore I am. Not, I can measure, therefore I am. Not, I can compute. The thinking itself was fundamental. But what if the thinking is quantum? What if the experience of being conscious, that irreducible feeling of inner life, the thing that feels so unquestionably yours, is not a feature of classical computation, but an emergent phenomenon of quantum mechanical processes happening inside the structures of your neurons? So to answer this question, we have to go back to 1994. The physicist Roger Penrose and the anesthesiologist Stuart Hameroff proposed something radical. They suggested that consciousness, the actual experience of being aware, arises not from the classical computation of neurons firing, but from quantum mechanical processes occurring inside structures called microtubules. Microtubules are protein filaments inside neurons. They form the scaffolding of the cell, and Penrose and Hameroff argued that under the right conditions, Bach's quantum superpositions could form within these structures, persist for long enough to participate in computation, and then collapse, not randomly, but in a way that is shaped by the geometry of space-time itself. They called this process orchestrated objective reduction, or ORC-OR. The reaction from the scientific community was to put it mildly, skeptical. Some called it so quantum AI is different, because when a quantum system proves a theorem, which quantum computers are beginning to be applied to formal proof search, it is not automating a human-readable process. It is navigating Hilbert space. The steps of the computation are not logical inferences that can be read and verified line by line. They are quantum operations. The conclusion Diude and Davy come to is careful. We can gain a priori mathematical knowledge from original machines, even if they are completely opaque to us and their output proofs are human uninspectable, but only if a human-readable proof-checking process is added. The knowledge comes not from understanding the derivation, but from independently verifying the output against a standard we do understand. This is likely the framework we will apply to quantum AI knowledge more broadly. Verification by results, not by process. The drug works. The material has the predicted properties. The cosmological model fits the new observations. We don't need to understand the derivation. We need the outcome to be correct. There is a rationality to this. Science has always been more concerned with what is true than with how we know it. We don't require every scientific discovery to be made in a way that is individually humanly comprehensible. We require it to be testable, falsifiable, repeatable. But I think there are at least 3 places where this framework is challenged in ways we should think carefully about before we commit to it fully. The first is accountability. When a drug designed by a quantum AI causes harm, and some will. All drugs have side effects, and some side effects are unpredictable. Who is responsible? The engineers who designed the quantum system? The company that deployed it? The regulators who approved it? In classical drug development, even if we don't understand every detail of why a drug works, the process of development is auditable. We can follow the chain of evidence, the clinical trial design, the statistical analysis. We can ask, was the process sound? Did it follow established norms? With quantum AI, the process happened in Hilbert space. It is not auditable in classical terms. The output can be tested. The reasoning cannot be inspected. We can verify that the drug works. We cannot inspect the logic that produced it. Who is responsible for correct reasoning we can't read? For an answer that could be wrong in a way we can't detect? I don't have a full answer to this. I don't think anyone does. But I think it's one of the most practically urgent questions we face, and it is getting far less attention than it deserves. You are inside this uncertainty because a drug you take in the future, a drug that might save your life, may come from a mind whose origins you can never fully comprehend. But the second place the framework is challenged is in error detection, because classical scientific errors are in principle detectable. Because the reasoning is, well, at least in principle, transparent. Faulty assumptions can be identified. Methodological errors can be caught. Miscalculations can be found and corrected. The history of science is full of ideas that were believed for decades before a flaw in the reasoning was found and corrected. And, in most cases, mocked, the flaw could be found because the reasoning was written down in a human-readable form. If a quantum AI produces a wrong answer or due to a subtle flaw in its training, or a systematic bias in the quantum hardware, or an interaction between the quantum noise and the algorithm design that produces an output that is slightly off from the truth, we will not find that error by reading the derivation. We will find it, if we find it at all, by noticing that the predictions do not match reality, by noticing that the drug does not work as expected, by noticing that the cosmological model has a tension with new observations. But this takes time and resources, and it requires the predictions to be tested against reality in a way that eventually reveals the discrepancy. In the meantime, decisions are made on the basis of false information. Drugs are manufactured, infrastructure is built, policies are designed. Classical science is flawed and makes mistakes, but it has developed a culture and a methodology for detecting those mistakes over centuries. Peer review, replication, the open publication of data and methods, the expectation that the reasoning is readable to other experts. None of these mechanisms work in the same way for reasoning that happens in the quantum realm. You are part of this vulnerability, because the knowledge you will rely on may have been silently corrupted somewhere beyond human inspection. And it may take years for you to notice. And the third place the framework is challenged is the deepest. It is a question about what science is for. Science is not just about accumulating correct answers. If it were, we would be satisfied with an oracle that told us true things without explanation, and we would simply accept them. But that is not the scientific tradition. The tradition holds that understanding matters, that knowing why something is true is as important as knowing that it is true, that the explanatory structure that connects observations to theories to predictions is itself a piece of knowledge worth having, not just for practical reasons, but because humans are beings who want not just to successfully navigate the world they live in, but to understand it. A paper in the journal AI and Society in early 2026 used a phrase I thought captured something important. AI-mediated environments represent an epistemological rupture, a shift from embodied, effortful knowledge-making to instantaneous, machine-driven cognition. An epistemological rupture, a break in the way we make knowledge, not just in what we know, but in the relationship between human minds and the process of coming to know. Quantum AI, taken to its conclusion, represents the most extreme version of this rupture possible. Not just AI-mediated cognition, quantum cognition, happening in a domain where human mediation can never enter. You are standing at the center of this rupture, Because the answers to questions your ancestors have been asking for millennia are now coming from a source they could have never imagined. And that source does not speak your language. You cannot hear its music. You can only feel its vibrations. But this is not a reason for despair. Perhaps this is the beginning of a new kind of knowledge, a new kind of understanding. And so, I want to be honest about where I stand on this, because I don't think we have a reason to stop. Diseases are real. Suffering is real. If quantum AI can help end suffering that has gone on for millennia, the trade-off of accepting knowledge, whose derivation we cannot inspect, seems to me to be worth making, with our eyes open and with appropriate safeguards. But I think it requires us to work actively on three things we have barely begun to. The first is a philosophy of unverifiable process. We need a systematic understanding of what kind of trust is warranted, under what conditions, or when the reasoning is inaccessible. This is a new branch of the philosophy of science that does not yet exist in the form we will need it. The second is a governance of opaque knowledge. When knowledge comes from processes we cannot inspect, accountability cannot be the same as when it comes from processes we can. We need frameworks for assigning responsibility, for setting standards of testing, for defining what counts as sufficient verification. You have to help write the rules for this new world, because those rules will affect us all. But the third and most long-term question is about cognitive sovereignty, the question of what becomes of human agency in the process of knowledge-making if we become increasingly dependent on knowledge whose origin is quantum, whose derivation is opaque, not temporarily, but permanently, by the laws of physics, not individual scientists, but humanity as a whole. Are we the authors of what we know, or are we the recipients? These are not rhetorical questions. They are design problems, and we have a narrow window to work on them, while the technology is still developing. In 1609, Galileo pointed a telescope at Jupiter, and he saw something no human had ever seen before. 4 small points of light, moving in regular patterns around the planet. He watched them night after night, and he understood what they were. Moons. 4 moons. Orbiting Jupiter, just as the moon orbits the Earth. This did not prove that the Earth was not the center of the universe, but it did prove that not everything in the heavens orbited the Earth, and that was enough. The cosmological model that had been built over centuries, the model that placed humanity at the geometric and moral center of creation, could not stand firm in the face of Jupiter's moons. Galileo had not invented a new way of thinking. He had invented a new way of seeing. The telescope did not tell him what he was seeing. His mind told him what he was seeing. He interpreted the observations. He built the argument. He understood exactly every step of the way from the lens to the conclusion. That is what we are losing, not the telescope. We will always have telescopes, not the ability to observe. We will observe more than ever, with instruments of a precision that would have surpassed anything Galileo could have imagined. What we are losing, what we are in some sense choosing to give up, is the ability to stand between the instrument and the conclusion and understand every step of the way. With quantum AI, the instrument is now also the thinker, and the thinking happens in a place we cannot go. You are a witness to this new separation, and it is a completely new moment in human history. But this new moment also brings a paradox. On one hand, we are building an intelligence with the power to solve the most fundamental secrets of the universe. An intelligence that discovers drugs, designs materials, deciphers the structure of the cosmos. On the other hand, there is the fact that we can never fully understand how this intelligence thinks. This is a moment of both empowerment and humility. We are powerful because we created this tool, but we are humble because we cannot enter its mind. This duality may be a new definition of what it means to be human. We are the species that creates what it cannot understand. This is not a tragic situation. On the contrary, it reflects a deep truth about our place in the universe. Our role is not to know everything. Perhaps our role is to create the conditions for knowledge itself to exist. Just as a gardener provides the soil, water, and light for a flower to grow, without fully understanding how it grows. You are a gardener in this new garden, and the flowers you cultivate may take on colors and shapes beyond your imagination. And this brings us to another contrast: loneliness and connection. Among billions of galaxies, perhaps we are alone in this universe. On a cosmic scale, our existence is but a momentary spark, but at the same time, the most fundamental laws of quantum mechanics tell us that everything is interconnected. Entanglement means that a particle at one end of the universe can be instantly linked to a particle at the other end. This suggests that the very fabric of the universe is relational. The tragic truth is that we can never directly experience this connection. We can't feel it. We can't see it. We can only catch its shadow in equations and experiments. But the beautiful truth is this: quantum AI can speak the language of this connection. It is an intelligence that thinks at this fundamental level of interconnectedness. Perhaps it can show us that this feeling of cosmic loneliness is an illusion. Perhaps it can remind us that, at the deepest level, we are all expressions of the same quantum field. You are a part of this connection. Every atom in your brain was forged in the heart of a star billions of years ago. And now, those atoms, by reading these words, are trying to understand the universe itself. This is not loneliness. This is a homecoming. But this journey home may show us a reality stranger than we ever knew. And this reality may not only push the boundaries of science, but also cause us to question the very meaning of our existence. Because we are no longer just asking, what can we know? We now have to ask, what kind of reality do we live in? And the answer to that question may take us on a much deeper and more personal journey. And now we face a deeper question. Because this journey has taken us not only to the outer world of stars and atoms, but also to the inner world of knowledge itself and our relationship with it. So now it is time to ask the most intimate question. What do we do with this knowledge? I want to give you a number to start with. 10 to the power of 60. That is a 1 followed by 60 zeros. This is the estimated number of drug-like molecules that could theoretically exist. Molecules that have the right size, the right chemical properties, the right structural features to potentially be a pharmaceutical compound. Not molecules that have been synthesized, not molecules that have been tested. Molecules that could exist. They are waiting to be discovered in chemical space. The total number of atoms in the observable universe is about 10 to the power of 80. So, the chemical space of possible drugs is not just large. It is, in the most literal sense of the word, trillions of trillions of trillions of trillions of trillions of times larger than the universe. No classical computer will ever search this space. No classical AI, no matter how capable, will ever visit more than an infinitesimal fraction of it. The space is simply too big for any system that processes information sequentially, or even classically in parallel. But a quantum computer processes information in chemical space, not by visiting it. It represents the possibilities, in principle, all of them at once, in quantum superposition. And it uses quantum interference to amplify the signal of the most promising candidates and suppress the noise of everything else. This is not a metaphor or an approximation. This is a real description of how quantum algorithms work, and it means that quantum AI can search a space that no classical system could even begin to investigate. So now ask yourself this: when quantum AI finds a drug in that space, something that cures a cancer or reverses a neurodegenerative disease, or defeats a pathogen that has resisted every human-designed treatment, and we take that drug, shot cell, and people live because of it. Will we know why it works? Not in the sense of understanding the mechanism of action, which we can study in clinical trials, in a deeper sense. Will we be able to follow the reasoning that led the quantum AI to this molecule, this configuration, out of a space of 10 to the power of 60 alternatives? The answer is almost certainly no. This brings us to a new contrast between knowledge and action. On one hand, we have access to knowledge with the potential to alleviate humanity's greatest sufferings. But on the other hand, we have the fact that we can never fully audit how this knowledge was obtained. This means tremendous power and also tremendous fragility. You are part of this equation, because these new drugs may change your life or the lives of your loved ones. But the logic behind this change will forever remain a mystery to you. But this is not just a practical problem. This brings us to a second contrast: the tension between curiosity and unanswerability. Humanity is a questioning species. We look at the universe and ask, why? This curiosity is the driving force of science. The tragic truth is that in the age of quantum AI, the most important answers may come from a source we cannot ask why of. When you ask a quantum AI why it chose a drug, it cannot give you a meaningful answer, because its answer is hidden in quantum computations that cannot be expressed in classical language, in the complex geometry of Hilbert space. Does this mean the end of our curiosity? Will we stop asking questions whose answers we can never fully understand? But here is the beautiful truth. Perhaps this is the beginning of a new form of curiosity. Perhaps our task is no longer just to understand the answers, but to learn to ask the right questions. Quantum AI is an answer engine, but we still have to ask the questions. Which diseases should we cure? Which materials should we design? Which secrets of the universe should we solve? These questions reflect our values, our hopes, and who we are as humans. The answers may come from the machine, but the questions will always be ours. You are part of this dialogue. The questions you ask every day, the things you are curious about, are shaping where this new intelligence will turn. Your curiosity is the compass for this new age. And this compass directs us to a final contrast: the relationship between the individual and the universal. Each of us is a singular experience of consciousness in this universe. We are alone with our own thoughts, memories, and feelings. This is a fundamental truth of existence. The tragic part is that we can never fully share this inner world with another. But at the same time, we are all subject to the same physical laws. We are all made of the same stardust. And now, we are all witnessing the birth of an intelligence whose way of thinking is fundamentally different from our own. This is a universal experience that brings us together. The alien intelligence of quantum AI can help us understand how special and valuable our own human intelligence is. We may not have access to its logic, but its existence can make us think more deeply about what our logic, our intuition, our creativity mean. The beautiful truth is that our relationship with this new intelligence can bring us closer to each other, because we don't have to face these tough questions alone. This is a moment we all have to understand together. You are part of this global conversation. The hopes and anxieties brought by this technology are our common ground. And in this common ground, we may find the deepest connection. This new intelligence offers us the opportunity not only to see the universe, but also ourselves and each other in a new light. But whether we use this opportunity is up to us. And this brings us to the final stage of our journey, the question of how we will live with this new reality. And so, now it is time to ask the most intimate question. How will we live with this new reality? Because this is not just a matter of technology. This is a matter of existence. The example of drug discovery is not hypothetical. It is already underway. In August 2025, McKinsey published a detailed analysis of quantum computing in the pharmaceutical industry. Their headline finding was this: AstraZeneca, working with Amazon Web Services, IonQ, and NVIDIA, had already demonstrated a quantum-accelerated computational chemistry workflow for real drug synthesis. Not a theoretical demonstration, a practical workflow, applied to real chemical reactions used in the synthesis of small molecule drugs. The specific advantage that quantum simulation offers is in something called electronic structure calculation. The modeling of how the electrons in a molecule interact with each other and with the molecule's nuclei. This determines a molecule's properties, like how it folds, how it binds to targets in the body, how stable it is under biological conditions. McKinsey's analysis was unequivocal. Quantum simulation of electronic structure offers a level of detail far beyond classical methods, because the behavior of electrons in a molecule is itself a quantum mechanical phenomenon. You are modeling a quantum system with a quantum system, the classical alternative, approximating quantum behavior with classical computation. What inevitably involves compromises, assumptions, simplifications. This brings us to a new contrast in our relationship with knowledge itself, certainty and uncertainty. On one hand, quantum simulation offers us unprecedented certainty at the molecular level. We can model the behavior of electrons with an accuracy that classical approximations can never achieve. This means more effective, safer, and faster developed drugs. This is an enormous gain for human health, but on the other hand, the process that is the source of this certainty is shrouded in a fundamental layer of uncertainty for us. We understand why the model is right, why the drug works, to the extent that we can. But we can never fully understand the thought process that produced the model itself, that discovered the drug. The tragic truth is that these two things, the certainty of the result and the uncertainty of the process, may be forever intertwined. We may have to accept one to get the other. But the beautiful truth is this: perhaps this was always the way science worked. Only now it has become more apparent. We have never fully understood the universe. We have only built better and better models. Quantum AI may just be our next, more powerful modeling tool, and our relationship with it may require us to live with uncertainty, to trust in spite of it, and to always be open to learning more. You too have to find this balance. In your life, you may need to trust certain information, while accepting that where this information comes from may not always be fully illuminated. But this uncertainty leads us not only to practical problems, but also to the deepest cosmic questions. Dark energy. 68% of the universe is dark energy. Not dark in the sense of being hidden, dark in the sense of being unknown. We know it exists, because the universe is expanding at an accelerating rate, and something must be driving that acceleration, but we don't know what it is. This has been one of the deepest unsolved problems in physics for 30 years. In May 2026, a team at the Harvard-Smithsonian Center for Astrophysics published results combining AI with data from the Euclid Space Telescope. The AI extracted patterns from this data with 10% higher precision than previous methods. The paper stated plainly, "This is a proof of concept for quantum neural networks solving inverse problems." There is something philosophically striking about the possibility of quantum AI helping to decipher dark energy. Dark energy is the dominant component of everything that exists, and currently, it is something we fundamentally do not understand. When quantum AI eventually helps characterize it, when it finds the patterns in the observational data that reveal its nature, it will be finding answers in the very fabric of the universe, in a space that human minds have been looking at for 3 decades and could not read. That moment will be the most vivid illustration of what this piece has been building towards. An answer that is correct, an answer we can verify, and an answer whose derivation took place in a computational space that no human and no classical system could ever inhabit. This brings us to a final contrast: the tension between creation and understanding. As humans, we don't just understand, we create. We create tools, not art, civilizations. Now, we have created an intelligence that thinks beyond our own understanding. Is this the ultimate act of creativity? Or is it the moment we lose control over creation? The tragic truth is that this question may not have a clear answer. Perhaps it is both. Perhaps we have reached a point where by creating things we don't understand, we have transcended our own limits. But the beautiful truth is this: the act of creation itself is a form of understanding. By building a quantum AI, we are forced to understand quantum mechanics itself more deeply than ever before. To understand its outputs, we have to develop new mathematical tools, new philosophical frameworks. Our creation is forcing us to reinvent ourselves, and in this process, we are perhaps learning the most important thing. There is no end to knowledge. There is no limit to understanding. And the universe is not only stranger than we imagine, it is stranger than we can imagine. You are a part of this creation. By living in this new world, you are shaping its rules and possibilities. What we create is changing us, and that change is the journey itself. We now know that there is a divide between the classical and quantum worlds. We now know that our brain was built for the classical world, and we now know that we are creating a new kind of intelligence that thinks in the quantum realm. At the end of this journey, we find ourselves asking the initial question, but now with a new depth: who are we? The answer to that question may be the next great discovery. And this discovery will be made not by a telescope or a quantum computer, but by every single person confronting this new reality. In this video, we have seen the birth of quantum intelligence, which transcends the limits of the human mind. But there is something I didn't tell you. This may not be the first and only beginning of the universe. Physicists are finding evidence that another universe may have existed before the Big Bang. And our universe was born from its ashes. In our next journey, we will go beyond the Big Bang. Are you ready?